Good afternoon and welcome back to the Open Hardware MiniConf. Many of the projects that we feature at the MiniConf are bare circuit boards, and if you're very lucky you might have a 3D printed case to go with it or a laser cut case, but sometimes there are projects that just take it to the next level. The talk this afternoon is going to be about the Mega 65, which is an epic project presented by Paul Gardner-Stephen and Martin Streit. So thank you very much for coming along. I am very excited to see how this project came about because the end result is amazing. So thank you very much and take it away.
Thank you. And thank you everyone for tuning in today. I hope that you're having a great conference and hopefully the next 45 minutes or so will be enjoyable and interesting as well. So with it, if you have any particular aspects as we're going through that you would like us to talk more about, we've asked the kind volunteers to kind of pop those through to us in as near real time as we can. And we would love to be able to be responsive in that way because we really want it to benefit all of you who are thinking about making open hardware. So the Mega 65, the project actually came about because I used to own one of these Commodore 65 prototypes that Commodore had made. So Commodore, who made the Commodore 64 and the 128 and the Amiga. And then when they went bankrupt, it kind of emerged that they had these kind of next generation Commodore 64s called the Commodore 65 in prototype form. And over time, they're now worth probably 10, 20, 30, 40, $50,000 on the market if you have one. And because I used to own one, and I sold it actually to do some work with the Serval project. And afterwards, I thought, it was really fun having one of those. I'd like to make one in FPGA. And so the Mega 65 is that process of saying, let's make a new Commodore 65 in an FPGA. And as we started thinking about what we wanted to do, we wanted it to be faster. We wanted it to be as compatible with the Commodore 64 as we could, and to really enjoy and be steeped in that Commodore 64 heritage. But we also wanted something that was actually just a joy to use, because this is, in our mind, this is the last 8-bit home computer that there is to come out. It's sat there for the last 30 years not being released, and we've kind of finished off, or are trying to finish off, what Commodore left undone. And so we wanted it to have a nice keyboard, good sound, and SD card for convenience, all those sorts of things, and really just to be as fun a machine as we can, and for it to be a fully open design as well. And I think, as most of us that come along to linux.conf, we're aware of all of the reasons why open hardware and open software are important. But in the retro community, we're also keenly aware because there have been projects that haven't been opened, and that as a result, you actually can't use the systems anymore. And so the C1, for example, was a Commodore 64 and FPGA that kind of suffered that fate, and you can't even maintain it now because it's closed. So the openness was really important to us from the beginning. So for those of you a little bit less familiar with the what Commodore made in the 1980s, so in 1980 they released the VIC-20, which was the first home computer to sell more than 1 million units. And Jack Tramiel, who was the head of Commodore at the time, his vision really was cheap and massive volume to get the price down, vertical integration, all of those sorts of things. So the VIC-20 was a great success. That then led to the Commodore 64. In true Commodore cost-saving fashion, they reused the case. And actually the first series of Commodore 64s even had VIC-20 keyboards in them as well. And that went on to be the massive success, and it still kind of has that place in culture today. And then a few years later, Commodore released the Commodore 128, which was a modest extension of the Commodore 64. And that also sold some millions of units. Interestingly, it was much less profitable for Commodore than the Commodore 64 was. But the story didn't finish at that point. There were rumours in the late 80s of Commodore making a next generation Commodore 64. And that was kind of hyped up for a while, and then it kind of died away, and people thought, oh, maybe they didn't do that. But in actual fact, Commodore did make a number of prototypes, and as far as we can tell, were probably only months off actually releasing the thing to the market before they completely canned the project. And so what we can see there at the bottom is one of the original Commodore 65 prototypes. And they have this distinctive kind of shape with a front-facing disk drive, the largely Commodore 64 keyboard with a few more keys at the top, and blessing upon blessing, the 4-way direction keys in a sensible kind of way. So it was quite an interesting machine at the end of that sort of 8-bit era. And so we set about trying to recreate it. And here in this image, we can actually see 3 of our different prototyping stages for the Mega 65. And we'll talk about all of the bits and pieces in this a bit more in a moment. And Martin will jump in that process as well. The top left one was our kind of cropped together prototype around the first revision of the motherboard that we made. And it's actually using a real Commodore 65 keyboard that we bought off eBay because there was a pallet of those keyboards, and I think someone in Eastern Europe bought them and kind of sells off some every now and then. So we originally actually were making the machine to use the real Commodore 65 keyboards because we believed that there was a supply. We changed tack on that later. The middle machine is one of the pre-series machines. So this has a second revision motherboard that had a whole pile of the missing things put in, we'll talk about. It has our full custom keyboard for the first time. And it has a vacuum-formed prototype case to show what it's like. And the one in the bottom of the screen there is actually, in fact, the one I have sitting here with me right now. And so that's the third revision motherboard, and that's with the actual injection-molded case, and again the full custom keyboard. So we've gone through this process to get to where we are now. It wasn't all just one go. And in fact, the very first iteration was not with a custom board. We actually started out with an off-the-shelf FPGA development board, so the Nexus 4, and this is actually what we implemented the core in to begin with. But always with that view that we wanted to go to a full custom board. And part of the reason that Martin is with me on the talk today, so I got to this point on my own, and I was having fun making this thing, but there was no way I was going to be able to make a complete finished machine. And then Martin and the other folks from the Museum of Electronic Games and Art in Germany, near Frankfurt, dropped me an email and said, hey, we love what you're doing with this Commodore 65 recreation. Would you like to partner with us to actually try and make the whole machine? And this for me was not a question that I needed to think about. It was just immediately, yes, it's much more fun with a group of people rather than on your own. And it was clear that we would be able to do much, much more. So the first prototype motherboard that was in that clear acrylic case, which actually was a display cover for something completely different. This was our first revision at the board, and so we kind of collected our design requirements together. And one of the great things actually that came about through the Museum of Electronic Games and Art was actually that they were able to reach out to some really good manufacturers and partners in Europe to say, hey, let's actually look at making something and doing something really interesting. Because, of course, there are many people who are about the right age to remember these 8-bit machines who are now in middle to senior management positions in these kinds of companies. And so, selling the vision of what we were trying to do to these organizations was one of the really great things, actually, that Mega was able to bring in quite early. And so this motherboard is made by Trends Electronic in Germany. And so they actually make the PCBs themselves, and they do the chicken picking and the circuit board design layout and everything. So they very kindly did the design for these and made us the prototype units. We were a little bit rushed, and so not everything we wanted was on there, including things like the SD card reader. That's what the wires that you can see on there are actually connecting up. But you can see we already have joystick ports. We have a Commodore 64 expansion port, a Commodore 64 disk drive port, VGA, digital video, 100 megabit Ethernet, and at the far end, at the top there, you can see the 34-pin black floppy connector to drive the internal disk drive, which uses a standard PC drive rather than a funny Commodore one. And then there's sort of debugger interfaces and power and the like. One of the other notable changes with the compared to the later ones is that the power jack on this one is on the side next to the power switch. On the later ones, we actually moved that to face the back, because we actually found that it made it much nicer on the desk to not have the cord kind of sticking out like that. And again, it was things that we were all able to do with the close partnership that we had. So as we said, we put it in the a leftover display case that I found at the uni. that someone was throwing out, just to have something to hold it, and the original Commodore 65 keyboard connected to that. And you can actually see in the box there's even more wires in there, because we realised quite quickly that there was a whole pile of things that we had left off that board, including more pull-up resistors than you can poke a stick at. But it was actually really helpful to confirm a bunch of design decisions and to be able to make good progress instead of it just being on the little Nexus board that didn't have any of these real ports. And again, you can sort of see some of the horrors in the case. And actually, the other thing you can see here on the genuine Commodore 65 keyboard, you can see that I've actually had to write the key labels on the top, because the keyboard that I got from eBay didn't have the top printing on there, because they had different variants for English and German. And so, of course, they had a whole pile of keyboards made that had neither, and then they would actually, they obviously would do the printing a bit later in the process. And so I kept writing on in pencil every 2 or 3 days the key labels, and so Q, of course, lasted a lot longer than the keys under the home keys and things, where you type more frequently.
And
so maybe I'll flip over to Martin now to talk about this one.
Yeah. So while Paul had in Australia the case that he made from found parts, let's say, we actually worked on getting the case a bit more to the more like finished product, and this was the first Mega 65 prototype that we showed at Amiga 30, which was an event in Germany, and you can still see the powers from the side. So this is the very first one, and there's also the Mega logo on it from the museum. And so we had that, and if you can go to the next slide there, we can sort of see some other folks that are in the team, and where that was presented, and people could try it and play with it. And there's a whole bunch of videos online. Some of it is in German. Some folks from the days of the Commodore actually visited there, and there's some talks there. And so that was that's about 5 or 6 years actually ago. And if we go to the next one, we actually have went back to the board and have now here the revision 2 board, and this one was intended to be feature complete, and most of the problems were fixed, but there were still some missing pull-ups. But we now have dual SD, so there's one in the bottom part, which is a full SD card slot, and there is a micro SD card slot in the top right that you can see. But we discovered a couple of things, that there's only a floppy drive interface that can connect it, but we wanted to have PC style wiring, and some of the details also Paul will jump in and correct me, because
so on the revision 1 we only had the motor and the select lines for the first drive on the cable, not for the second drive as well, so we fixed that on this second one, I think.
And then it was a couple of other parts. So, and now we have here the RTX 7 100T as an FPGA on that, and what is on that board still is a chip for the digital video, which we actually later removed in our next
and we'll
iteration.
Talk about that, yeah.
Yes, and so that actually produced quite a headache, and we're basically talking about digital video you might know as HDMI, and getting that to work is quite a drama, which we see on the next slide there.
Yeah, so it was a massive drama. So we thought, okay, we'll do this the safe and sensible way. So we spoke with Trends and said, what part would you recommend to produce HDMI compatible video? And they said, you should use this one. We use it in a number of projects and it worked perfectly. And so we thought, okay, yep, excellent. And there was lots of instances like this where having the partner of Trends was actually really helpful to make design decisions for the board. But what we found was that this particular chip doesn't work properly at 480p and 576p. It produces perfect HDMI at higher resolutions, but it's just my feeling is that they probably hadn't connected it to a protocol analyzer at those low resolutions and confirmed that the HDMI audio worked properly, because this is actually what the problem was, that the audio would work on some monitors, not others, and then other monitors would, pardon me, show a display and or sound for a while, and then the screen would go blank for half a second and come back again. And it really varied on the model of monitors. It was really, really painful. And so I think we spent, about 10 months, maybe even longer, of me pulling my hair out trying to, look at all the I2C programming information for this chip. And, have we left something out? We couldn't use the official driver because we had no embedded, Windows or Linux operating system, because the Mega 65 is pure FPGA implementing an 8-bit system, which was one of the design goals that we wanted. There is no big CPU, if you like, in there. And so this is one of the areas where that was a little bit annoying, because we couldn't just easily, run their driver and go, look, we did it and it doesn't work. ADV were quite helpful on their forums. And if you look at the Mega 65 blog, you'll see there's some discussions that we had with them around that. In the end, we took a bit of a punt. We knew that there were some other projects that had full open source HDMI compatible implementations in FPGA, just using the differential lines from the FPGA directly. And so we thought that this would be the best way to do it and just get rid of this chip that was causing us problems. So we ordered a cheap FPGA board that had that wiring on it, but didn't have a big enough FPGA to run our whole core. So we had to kind of cut it down and just do a test. And so that was more compatible, but it still wasn't perfect at the time. But we had to make a decision. Did we think we could get that one right, or did we think that we could get the one with the complex proprietary HDMI driver chip to work? And in the end, we made the right decision, which was to go with the full open implementation, because we could indeed debug it. And I've been keeping an eye out on eBay for a while for HDMI protocol analyzers. And the final end of life support for Windows XP was a blessing, because there are these Digilant protocol analyzers that will do HDMI 1.4a, but they only work on Windows XP. Nothing newer, nothing older. And so through the university, I had to arrange to get access to a Windows XP license and put it in a virtual machine. And fortunately, all the software for it worked, but it meant we could get the protocol analyzer was under $1,000 instead of about $15,000. And after having spent about 3 weeks trying to get the pure FPGA implementation of HDMI working and only getting it mostly working, it was 2 or 3 days, I think, Martin? And we had perfect, flawless HDMI compatible output. So we're now in this really interesting situation. So we're not licensing the HDMI trademark for the Mega 65. We don't need to. You can use any shape connector you want. But we can actually say that it's HDMI TM compatible, because we've actually put it through one of the official protocol analyzers that are actually used for HDMI compliance testing. So we can say that it has an HDMI compatible display output. And that whole process was, as I say, that was the better part of a year of just pulling hair out. In the process, actually, there were some changes we had to do to get to that with the clocking and everything in the FPGA design. But that's a whole other story. We're happy to talk to people about that, but less interesting from the hardware perspective. So all of that, as I say, was finishing off while the revision 3 circuit board was being designed during COVID lockdown, and while I was living in the middle of the outback. So this was logistically a really interesting kind of process. So Martin and the guys in Germany were liaising with Trends to get the various remaining fixes put onto the board. And we'll do a little bit of a tour of the board in a moment. Martin can pan a camera around and we can actually talk about what's on the board. But so that board was getting made, and the postal system to deliver, so we were living at Arkaroola, the very top of the Flinders Ranges. For the post to get there, it goes to a private bag in Port Augusta. From there, it hopefully and usually gets into the right locked bag. And then the locked bag gets transported to Copley on a Friday and on a Wednesday. And then all going well, on a Monday and a Thursday, we get the post actually physically come out to us there at the village. And then we actually have to kind of walk in from where we're living out in the house, about a kilometre away, into the village and check whether there's any mail for us. So it's a little bit of a convoluted process. And if it ends up in the wrong bag, as we had one parcel, that ended up in a bag going to William Creek. So it went from Port Augusta to Coober Pedy to William Creek. William Creek said, this isn't for us. Put it back in the bag to Coober Pedy. Coober Pedy said, what on earth is this doing coming to us? This should have gone to Port Augusta. They sent it back to Port Augusta. Port Augusta sent it back to Coober Pedy. Coober Pedy sent it back to Port Augusta. Port Augusta eventually sent it up to me. And so it took 4 or 5 weeks to get some bits and pieces through. The motherboard, fortunately, I think came through within a fortnight. But again, we were so crunched for time at that point. So I had to work on doing the FPGA and the board bring up remotely with the guys in Germany. So I would generate a bit stream and they would test it and tell me whether the a particular board function was working, so that we could, if we had to, we could get a 4th revision of the board made in a timely manner, because what we had ticking was the dev kit stage that we wanted to do. We wanted to get 25 machines into the hands of developers, hopefully, and also to generate a little bit of additional revenue for us for the kind of finishing tasks and things that we do. And we were totally open with the community about that, and they were really good and supportive with that. And so, yeah, we had this kind of whole bit of time crunch. And then the board turned up, and we actually had it 90% already working. And then it was just the remaining bits and pieces that I needed to do from where I was. So it's actually the time zone difference is a problem at times. Fortunately, I'm often up early and the guys in Germany are up late. And so it usually works out fairly well. And as I think many of us in the open source community know, that you can have a distributed team, and if everyone is on the same kind of page and you know how you're working, this can actually work really, really well. So maybe, Martin, would you like to start doing a tour of the board with a camera, and I can talk about the components as we move around?
I can do that.
Okay, yep. So apologies, I'm going to be looking across to the side so that I can see what Martin is showing here.
Yeah. So
look at that.
Also, what we're seeing is an R2 board. So all the R3 boards went to developers, and so I only have an R2 board here for the presentation, but that's totally fine. And Paul, you can also direct me to certain things.
Sure. So I guess start in one corner, and we'll just we'll work our way around, I reckon.
Okay. Well, I guess from our connections from the outside, I guess power.
So what we have on the side, power, and the 2 joystick ports. So these are standard 5-volt Atari Commodore style joystick ports. Now, actually, one thing that we did realize, and this is a bit of a bummer, is that we didn't think about some funny things that can go in the joystick port needing 2-way communication. So the joystick ports are input only on there. Now, what we did implement on the revision 3 board was support for the Commodore 64 mouse. The Commodore 64 mouse is the most bizarre thing, because Commodore tried to come up with a way to make a mouse that would work on a standard Atari port without needing a lot of CPU power. And so the way it actually does it, it pretends to be a pair of paddles, and there's a microcontroller in the mouse that decides how long before it starts pumping 5 volts onto the analog input on the joystick port, timing it precisely so that the analog to digital converter in the Commodore 64 can read out that, it can actually read out a 6-bit mouse position for X and Y each iteration. So we had to implement that logic, which was a little bit complicated, but we were really happy that we've got that working. And the reset button, of course, in that bottom corner is just a convenience. The Commodore 64 never had one, the 128 did, and every later computer that Commodore made in the 8-bit line certainly had one, because it just made life so much easier. And right next to that there, next to the screw, is an internal speaker connector that we've put on there. On the revision 3, there's 2 of those for stereo now. And we actually need to do on the revision 4, or whether we can do it with a component change. We've got a problem with the audio filters on that, so if anyone does DSP work, we'd love to hear. The filter we've got isn't actually filtering out the high frequency noise, and that makes the speakers get hot as they get 100 kilohertz or even megahertz kind of speed coming through. There's the next little connector there, 4-pin connector, is basically an I2C header that the guys at Trends just added they said, oh, if we put something like this on, then people can make other kind of interesting expansions. And so we were totally happy to have that on there. In the middle, we've got the battery for the real-time clock, which is next to that cable connector. Is actually the real-time clock chip, and then the cable connector is to the keyboard. So unlike the original C65 keyboard, we actually use a serial protocol to talk to the keyboard, but the keyboard doesn't have a slow microcontroller. It has another little FPGA. So our main FPGA on the main board is a Xilinx. This one is a Lattice. So in fact, that could be done with full open tooling. The nice thing with that is that we still have effectively zero latency on the keyboard. So I think we get a keyboard update every 50 kilohertz or so. So, you know, there's of the order of 20 microseconds of delay on the keyboard, which compares, of course, very favorably to USB keyboards that can have, you know, milliseconds and potentially many milliseconds of delay. Okay, so the big chip next to the red LED is the main FPGA itself. So the revision 2 board is a little bit unusual. It's got the 100T FPGA from Xilinx. The revision 3 board, we've actually managed to go back to having the 200T, which is a much bigger FPGA, which we're really happy about. So that's going to let people port many more different cores to it. So we can have an Amiga core without needing any external RAM, but we do also have an 8 megabyte external RAM on there. Okay, so we've then got the internal SD card slot, which has just moved out of view. Next to that are 2 standard PMOD connectors that are directly connected to the FPGA. So you can put interesting things on there. A couple of LEDs, which of course we've got blinking. The chip you can see in the frame here toward the bottom, next to those 2 headers, is a third FPGA. So Trends put this one on so that we basically have brick proofing for end users. So this FPGA can read a bit stream from an SD card and can feed it to the Xilinx FPGA, at least when we implement the bit stream to do that. Because again, there's no big CPU on here to do that for us. To the left of that is the debug connector for JTAG for that Max 10 FPGA. So indeed, it's a Max 10 FPGA from Altera. So we've got an Altera, a Xilinx, and a Lattice FPGA on this project, which lots of hard disk space for the software. And then with the green spot, that's the debug connector for the main Xilinx FPGA. So that's the Digilent Trends style connector. And yeah, that's just for JTAG, and it also has a serial port. So the Mega 65 has a serial debug interface right back from the beginning. So that's available on that via USB, which is really comfortable for development. On the lower right, we've got the 34-pin floppy connector, which we know about, and 2 power connectors with 5 and 12 volts on them, which of course can be used for floppy drives or indeed for other kind of internal expansions. So there is plans to make an internal expansion board that would have, you know, for physical SID chips and some of the missing Commodore 64 ports that we didn't port on the main board to keep the price under control. And so that might then draw 12 volts from there, for example, to power SID chips, and that will be fine. Now to the left of the green spot, we've got the 100 megabit Ethernet. And again, there's no microcontroller. This is direct connected via a PHY chip into the FPGA. And we have our pure VHDL open source 100 megabit Ethernet controller, which is then available to the 8-bit computer. So this is probably the fastest 100 megabit Ethernet that you can get on any 8-bit machine. Super low latency and all of that kind of thing, because it's all pure in the FPGA fabric. The micro SD slot to the right of that, so you can have 2 SD cards, one that's easier to change from the outside. To the right of that is the audio jack. We got the wiring wrong on the Rev 2 board. We fixed it on the Rev 3 board. Then to the left of Ethernet, we have the HDMI compatible video output, and then we have the VGA output, and they can both be driven independently by the FPGA. Yep, so you can see the ports there on the back. So this is actually useful. We could actually put a debug interface on one and have the live display on the other, because we have this kind of matrix mode thing in the Mega 65 that we've shown before, where it's hardware composited by the FPGA, so you can debug and change memory and view memory, and that's all good. But also, if when we make a 128 core, 128. The Commodore 128 was unusual in that it had 2 video outputs that were independent, one for 80 column, one for 40 column. And some people who use that system really like that feature. And so we can actually do that on the Commodore, on the Mega 65, because we have these 2 fully independent video outputs. Then to the right of that, we have the Commodore 64 disk drive port. So this is Commodore's infamously slow IEEE 488 without all the speed connector and the expansion port. And I think that's pretty much got us the lap around the motherboard. And yeah, so it's the yes. It's a. No, let me just check the next slide whether we're up to that. I'm just going to hop through a couple of the slides. Okay, stay on, Martin. We'll talk about the injection-molded case before we move on to the dev kit. So Martin, if you can show me bring that back into frame. So what Martin's got here is one of the first shots that came out from the injection molding process for the cases. And so because this is what's going to be the final cases. And so we can see we've got the same ports. Now just move it across toward the other end. And we've got these cutouts. This was when we did the planning for the expansion connector. So the big one on the right is for a user port, Commodore 64 user port. Then it's composite video output, Commodore 64 style. The next little one is for the Commodore 65 disk drive expansion port, of which I think there are 2 known disk drives in existence, but someone reverse engineered the board. And then the last one is actually for Commodore 64 tape port, or just whatever people jolly well like. And so we wanted for people to be able to pop these things out without having to, hack the case to pieces. And we were able to get screw bosses and things put everywhere to support having the boards. We can have a board there and have it really well supported for that. So thinking ahead for these things before the hardware gets hard to change is really worthwhile. So we'll come back to how we got that case made in a moment, but we'll go via the dev kit process. So what we've got here is one of the dev kit machines. So this is with the Rev 3 board that has all of those corrections on it, which is the current revision, in an acrylic case made by Plexi Laser, I think, isn't it, in Germany?
Yeah, and
yep.
to give a little context, so the what you see there with the process of making the case is many iterations. It's another manufacturer actually in Austria that we found, and when you do an injection molding, so if that's not familiar to everyone, is that you get heavy machinery and you mill out of a big block of metal the form, and you put then the plastic in it in a hot state, and then press it, and then you get out the case. And these tools, the tooling is super expensive, and so you also want to get it right. And the tooling, we actually started a crowdfunding for that, and we assumed that it will take us quite some time to actually get the funds together, and that this would give us actually at least a year or more to continue working on the FPGA side. And so the idea was, okay, so we have a board, but we want to get this out to the community so they can also develop on the software side. So, but just giving out a board was like, that's not super cool. So let's figure out another way of how we can get a case made early. And of course, people would probably think also about 3D printing. We did also that. So there are some 3D printed prototypes, but it doesn't work well for such a case in that size, or it's also quite expensive in that number that you want to get. So we went through these stages to actually see what we could do, and then also spoke back and forth with a tooling manufacturer while having a crowdfunding. And with the crowdfunding, we didn't actually go for any of the major platforms because we were like, oh no, we don't want to give someone the percentage, and also we don't want to have this 30-day limit or something to get this done, or you're not funded or something. So we actually went retro style and made a high score board and said like, here you can like put in some coins into sort of the machine to play game. And we started that in end of 2019, and what is it, 65 days or the square sum, we actually got this all funded, which was kind of interesting because the community looked at it and said, like, after like a couple of weeks or like 2 weeks or something, oh, if this goes like on like this, it's going to be 2030 or something until the funding is there and we produce a case. We didn't include the graph, but you can find it online. It's like, it goes like a line of, okay, here's the funding, and then it goes like this. So someone was sort of super enthusiastic and actually just finished the funding super fast, and we were like, oh, okay, so now we can actually produce the mold. And for this mold, we're talking about 60 to 70,000 euro. Just to give you a perspective. And that was for us something, okay, we can't kind of pay this up front, so we actually asked the community, and the whole project is with the community. But on the second track, we need to get out some boards that are also produced so we can figure out what's going wrong. And this is where Plexi Laser came in, and they produce cases for various retro machines out of acrylic glass, and they cut it and bend it and have some fun processes. And they made one custom for us in that case. And we could get 100 dev kits out last year, end of last year. And so this is what you can see here, and it's in a nice acrylic shape. And it's also smaller, so the floppy drive is on the side. Some people really like that. We might consider this small form factor for future releases, but yeah, that's kind of what you can see here. And maybe we continue to the next slide there. So this is another team member. This is Anton. And here it's a 15-minute video of how to assemble this dev kit, and this is online. One can see it and can have some fun. There's one with music, there's one where he's only talking, because people needed to assemble that. And from the dev kit, we also want to talk about some other parts that are there. The keyboard is one of the main features. It's your user interface on the retro machine, and this is something that is super important. And so on this, there were a couple produced for the pre-series, and now we produce some for also the developer kit. And I don't know, it's basically the standard C65 keyboard, and it has super nice keys. And if we go maybe to the next slide, I can also say something about...
So I was going to say with the keywords, we're running out of time. I think people have got questions. I think we've got 10 minutes, including question time left.
Oh yes. Okay.
So we might just, on the keyboard, say a little bit more and then wrap it around. So, cool. So for us, the three key pieces were the motherboard, the case, and the keyboard. And for the keyboard, some other retro projects have kind of made... It's quite an understandable compromise of using a standard PC 104 layout or one of these other standard layouts and putting custom keycaps on a mechanical keyboard to get, most of the way to the original. But we wanted something that had the fidelity to the original in every way. And so we actually, with GMK, went through the process of actually making this full custom keyboard. As I said, it's got a CPLD and FPGA on the back rather than a microcontroller. It has the layout we want, and the lock keys was a little bit of a drama. We couldn't get the locking Cherry MX keys anymore. You used to be able to get them, but we can't anymore. So we instead went for ones with we put an LED in, so we can actually see whether it's on or not. And we used the clickiest MX keys we could find compared to the less clicky ones for the rest of the keys. So there is a tactile difference. You feel the difference of the lock key, just like on an original 8-bit machine, and you hear the difference. And with the light, this is just a really nice end result. And the other thing that we're able to do with working with GMK is that we have the front printing on the keys, just like the original, rather than kind of the cheaper way of putting those symbols on the top. And those keys are double shot molded as well, so that you never rub the thing off. So everyone who handles the Mega 65 keyboard just falls in love with it and says, "Oh, why do I have to do cross development for this machine? Why can't I just type on the keyboard directly?" And for us, actually, that recreating that joy of the 1980s, getting a home computer experience is what we set out to achieve, and we've put a lot of hard work into it. But it's just blown us away at how much people have really kind of enjoyed that experience. We've got people who are sort of saying they haven't enjoyed coding this much for 30 years as they kind of go through that process again of rediscovering what an 8-bit machine is capable of, and the simplicity of that, and having the beautiful form, and it just feeling right and nice, and you turn it on and it's on, and all of those sorts of things. So before we move to questions, I just want to, as always, to the community, this is an open source project. The community is actively working on making software for it, on documentation. The documentation we've also put a lot of work into making beautiful as well, in the original style. It's now nearly a 1,000-page book. It's just really fun to work on. And if you have kind of retro nostalgia, then drop us a line, or if you just want to come and have a look, if you go to mega65.org, there's a link to our Discord server there as well. And we'd love to welcome more folks to to come and join us on this crazy journey of making something which is it's a piece of history, it's a piece of art, and it's just a really fun geeky kind of device. Did you have anything last you wanted to add, Martin?
No, I guess we can go to questions and see what people want to know more about, and then we'll just do that. So I think if Jonathan wants to join and relay those questions, because otherwise we will talk for hours.
Yes, I'm back. Okay, we only have a couple of minutes, but there are quite a few questions. Because I'm going to start with one of my own, which is really a personal question. There are many reasons for doing a project like this. What are personally for you, Paul and Martin? Why did you undertake this?
Lots of reasons. Part of it was just seller's remorse at not having a Commodore 65 anymore. Part of it was just fun. I always wanted to make a Commodore 64 accelerator, and FPGAs got big enough and cheap enough to do. It was all about fun from the beginning for me, I think.
Okay, great. And Martin?
I joined the Museum of Electronic Games and Arts as a photographer at some point, and I'm not in the C64 generation, so I didn't experience this as a child or as a teenager or something. And I photographed all this old hardware from them. And I was part in the beginning, then I dropped out a little bit, and then I joined back in. And I'm doing lots of video stuff, photos, and also now to actually make this and to work with all these companies, we set up also a small company entity so we can actually do this in legal and tax and whatever, all these things. When you work with lots of money and with big companies. And it's just a community project out of this museum, and then also with the folks, and to actually make a dream happen. And we're working on this for now 6 years. So it's just continue till you actually can finally release it. So that's just why we're doing that.
So it's an obsession. That's what you're saying.
I guess so, yeah.
Great. You mentioned setting up a company and all of that sort of side of thing. That ties into a couple of questions. So James Sinclair asked how much was the tooling for the case, and at some point you mentioned a fee of I think 60 to 70,000 euros. Is that was the figure?
A little over 100,000 Australian dollars, and that was cheap for getting it done properly. So this is a really interesting point. We could have done it cheaper in China, but then we wouldn't own the tools and have control of them. And as it turned out with COVID, that was a very good decision to make.
Been a problem.
And likewise, our circuit board manufacture happens in Germany.
Okay.
So we were talking to some of the other retro projects, and they were just,
dead in the water.
Because the Chinese companies are saying we're not taking on any little projects for the next year. They're focusing on the big stuff to keep them going. And to simplify things. And so, by aiming for quality, rather than price, there are other benefits that have come in from that. And so for small volume, it's not a bad way to do it anyway. But it was the partnerships with those companies that the folks at Mega were able to establish that have led us, to make a made in Germany retro computer in 2021.
Fantastic. And James Cameron asked about the cost of the acrylic proto case that you made.
That was a lot cheaper, Martin. Do you remember? I think it's the order of €50 a piece or something.
Yeah, something like that.
Yeah, something. Don't quote the exact figure, but it's something like that.
Yeah. Okay. So the Commodore 64 obviously has a very big fan base and many people that are obsessed with it. So there has been a lot of work to retrospectively document it, but are there particular sources of information or resources that you found useful when you were looking at things like the Commodore mouse interface and understanding how that works?
So Michael Steil, pagetable.com, has a great blog where he kind of goes through a whole lot of, picking aspects of the Commodore 64 apart in minute detail. He's always a good read. And some of it was just looking at the original Commodore 64 documentation is actually remarkably thorough. And it's an approach we've tried to take with the Mega 65 documentation. Our chipset guide is now 500 pages or something long alone, and it's not finished. And so that level of detail, we had all the timing diagrams, everything of how it worked. And so we were able to hack around with Arduinos and things and actually make a replica mouse and make a replica mouse controller and show that we could actually do all of that.
That's fantastic. Well, we're pretty much out of time, but I have one final question for you, which is there anything else you want to achieve with this project, or are you done at this point? Where is it going now?
Tune into my talk tomorrow about digital sovereignty and also the megaphone, which is kind of linked to that. I'm not sure whether we can get the image up if I plow through to the end here somewhere. We were overly optimistic. We've got a great solitaire port, by the way. This actually looks fantastic and is super responsive. User guide, and where's the... It's going to take me so long to get to the slides. Here we are, circuit board for the megaphone. So we're making a pure 8-bit smartphone that's secure and fully sovereign.
Oh, that's amazing.
More about that in the talk tomorrow.
Yes,
working
okay.
touch screen, the whole lot.
Everyone go to that talk tomorrow. Fantastic.
Yep.
Well, we're out of time, but that was a fantastic presentation. Thank you, Paul and Martin. I really appreciate your time coming to share this with us. So,
my pleasure. And thank you all for listening.
If anyone who is watching is interested in following up this project, have a look at Mega 65. And I believe you have a Discord and other resources of information.
In the little nav bar at the top. You'll find the Discord link. We'll be there for a little while straight after the talk.
Perfect. Thank you very much. And to everybody else, we will be back in about 10 minutes with the next talk.